Hey, AP Calculus students, this is Mr. Gilson. Here is your homework for integration of logarithmic and exponential functions. So since you guys are all capable calculus students, I'm just going to invoke FTC to identify the rules of integration for exponential and logarithmic functions. It should be pretty clear that the integral of e to the x is going to be e to the x, and the integral of 1 over x is going to be the natural log of x. And that's almost complete, but we'll fill in a couple of additional details in just a sec. So the integral of e to the x is going to be e to the x plus c. The integral of 1 over x is going to be the natural log of x. But notice I've added something a little bit extra, the absolute value. And I also left off the c. Oops. This is indefinite integration. So let's talk first about where the absolute value business comes from. If you just consider the general shape of a logarithmic function, whether it's the natural log or a log of some other base, it's always going to have this kind of shape, and it's not going to be defined for negative x's. So that means that if we're actually doing some integration that has a negative quantity in it, whenever we integrate it, we can only evaluate that quantity when it's the positive version or the absolute value. So the first thing to consider anytime we're integrating is remember that when we integrate, it has to be the integral of the outer times the derivative of the inner. And although the integral of e to the x is e to the x plus c, what about e to the 2x? The integral of e to the 2x dx is not quite in the form the outer times the derivative of the inner. If we think about rewriting this integral, we could rewrite it as e to the 2x. And we know when we take the derivative of the inner, the composite function, the derivative of 2x is going to be 2. So we need to see a 2 in there. And of course, the derivative of x, we call it dx, even though that's not precisely what it is. Now, we introduced that 2 for our purposes so that we could integrate. So remember, we have to undo that math by putting a 1/2 coefficient out front. So we have not changed the value of the integral. And now we have it in the form the outer times the derivative of the inner. So we can integrate it just using the rule. So that's going to be equal to the integral of e to the 2x dx is e to the 2x. And then we have to bring that 1/2 coefficient down. And then our plus c, since it's indefinite integration. Can you do the other two? So in this example, we know that in order to get it to the integral of the outer times the derivative of the inner, it's going to have to look like something like that. We still have to account for that entire 9 that was in the original problem, so we factored 3 out to go into the 3 dx, leaving 3 behind. So that value is 3 times e to the 3x plus c. You may recall at times in the school year, I may have accidentally given you guys some integration problems that you weren't able to do. This would be a good example, where you would restate this as a power, anticipating that you'll use the power rule to integrate it. But when you use the power rule, this 3x plus 5 is going to become 3x plus 5 to the 0th power, which is 1. And you know that just a quick glance of the graph of this function will tell you there is no way that the integral is 1. So the reason that you were not able to do those is you hadn't yet learned the logarithm rules. So if you have an integral in that form, that becomes the natural log of x. And again, we're going to use the absolute value because of the domain restrictions on the natural log, and then plus c since it's an indefinite integral. So in keeping with integration more generally, we all need the integral to always be expressed in the form of the outer times the derivative of the inner. And when you're looking at problems like this, you have to recognize that the inner is the 2x. Now what's important about that is that when you employ the chain rule and you need it in the form of the outer times the derivative of the inner, you're not going to have a derivative over here of 1/2. You're going to have a derivative of 2 because it's the 2x that is the inner function. At first, it may be tempting to look at that 1 over 2 and imagine that you have to use a 1/2 as the derivative, but that is not the case. So let's work this one out. So I'm going to emphasize that 2x is that inner function by putting parentheses around it. So we know that this integral has to be in the form 1 over 2x times 2 dx in order for us to integrate it. And since we introduced the 2, for our purposes, we have to multiply by 1/2 out front so that we don't change the value of the integral. And that becomes the natural log of 2x plus c. Can you do the next two? So the second question here would be set up this way. And that integral is going to be equal to 5/9 times the natural log of the absolute value of 9x plus c. Now, like in other indefinite integration problems, remember that the constants, although conceivably you could distribute those constants into, or I'm sorry, those coefficients out front into the constant, but we don't bother doing that since the constant is just arbitrary anyway. So remember, this technique we called integration by substitution, or more specifically, integration by U substitution. And it's all about I spy with my little I. On some of these, it becomes really apparent when you look at this. You say, oh yeah, I can see the inner function, so I can recognize that I'm going to have to use the chain rule. I'm going to have to think of this integral as being the integral of the outer times the derivative of the inner. So the second part of the fundamental theorem of calculus, of course, applies anytime that you're doing definite integration. So again, we'll use the U substitution methods to integrate this. And then valuating is just like before. So we'd have what? 1/2 times the natural log of 2e minus 1/2 times the natural log of 2. So on an AP free response question, you would not have to simplify this, even though the rule that I've told you up until now is eliminate all of the letters. Well, the fact is you can leave natural log expressions or log expressions in there. You don't have to simplify those. Let me use a trig example to remind you of some of the patterns that you had to recognize when you're integrating. You may recall in a problem like this that when you recognize cosine is to the second power, actually -2 power, and sine, or negative sign, is the derivative of cosine, then you can rewrite this as an integral of cosine x to the -2 power times the derivative of the inner, which would be minus sine x dx. And since we had to introduce the minus, we'll have to put another one out front. And then whenever you integrate that, you're just integrating using the power rule, and that becomes negative cosine x. I'll do it to the -1 power plus c. Well, there's some tricky looking problems kind of like that whenever you're doing exponential functions. Here's one of those tricky problems. So when you look at it, you should be able to identify, okay, we've got some natural logarithm going on, and then we've got some 3x business going on here. And in the same way that on that trig problem, you had to identify which was the outer and which is the derivative of the inner. And the same is true here. So you can either think of this 1 over 3x as being the outer, and then the natural log of 3x being the inner. Or maybe you should be thinking about the 1 over ln of 3x as being the outer, and the 1 over 3x is the inner. So when you look at that relationship between the 3x and the natural log of 3x, hopefully it'll come to mind, oh, the derivative of natural log of x is equal to 1 over x, and that should be able to guide you to apply the chain rule in this situation to set up that integral. Try to do it yourself. So did you deduce that the natural log of 3x is like the integral, and then the derivative of the inner is the 1 over 3x? Because the derivative of the natural log is 1 over x, and the derivative of the natural log of 3x is 1 over 3x. A bit tricky, but it's even tricky when you evaluate it. Where do you go next? So the integral of 1 over the natural log of 3x is going to be the natural log of whatever that is, and that's the natural log of 3x. It's kind of tricky, isn't it? Of course, we have the 1/3 out front to account for the derivative of the inner, and then you'll have your plus c. Even the tricky problems with integration of exponential and logarithmic functions are usually pretty straightforward. This one, for example. Can you use I spy with my little I and see the inner function and then the derivative of the inner function? Well, the parentheses are almost all a tip-off to the inner function. So if you think about this being the integral of 1 over 3 plus 2e to the x times, and we need the derivative of this inner, and the derivative of the inner is going to be 2e to the x dx. Now, we had the e to the x in the original problem to give us part of the derivative of the inner, but since we had to introduce this 2, we'll have to put a 1/2 coefficient out front. And now that becomes what? The integral of 1 over that is going to be the natural log of the absolute value of 3 plus 2e to the x plus c And don't forget our little 1/2 coefficient out front. That's about as tricky as they get. Try this one on for size. The trick here is seeing the function and the derivative of the function. So if we think about this as the integral of e to the x to the 5th power dx, it starts to look like an integration that we can use the power rule on. Except that if e to the x is our inner function, where is the derivative of the inner? Well, what you can do is you can take that e to the x power to the 5th and you can split it out into e to the x power to the 4th times e to the x power dx. Now can you see how to integrate it? It's just a straight up power rule problem. So that becomes e to the x to the 4th. That's going to become e to the x to the 5th power, the power plus 1, plus c, which is e to the 5x plus c, which is exactly what you would have gotten if you just applied the rule arbitrarily to the integral. So it's nice to know that, hey, it all works out either way, whether you do it by substitution or just use the rule. It's part of that elegance of calculus. So let's look at the classic FTC problem. So suppose you have this integral, and you're asked to determine what the derivative of that integral is with respect to t. Well, remember the idea behind FTC was it's like the derivative and the integral kind of cancel each other out, and then you end up doing substitutions into whatever the integral is, substitutions of t and substitutions of 5. But remember, when you take the derivative, any place where you'd substituted that 5 had become a constant, so when you take the derivative of that, it goes away, leaving you with the derivative of this integral is just e to the 3t. So, do you remember how to do the FTC problems whenever you were making a substitution that was more complex? In fact, think about this. It's going to be a chain rule problem because you're substituting a function into another function. Can you get the answer? So as before, the lower limit of integration 5 just falls away since we know that after we integrate and take the derivative, the constant will go away. So now it's just about substituting this 2t squared where the x is. So that becomes e to the 3 times 2t squared. But we're not through yet because remember, we turned this into a composite function, and when we turned it into the composite function, when we differentiate, then we would have to employ the chain rule. So that times the derivative of the inner, which would be 4t. Is that ringing a bell? Question? So consider this FTC problem. Do you remember what to do whenever the constant is up top and the variable is down bottom? Remember, in this case, we're going to end up with the natural log of 3 times 5t squared times the derivative of 5t squared, which is going to be 10t. And since the variable is in the lower limit of integration, when we applied the FTC part 1, we would have big F of 8 minus big F of 5t squared, and that negative sign in that expression would have to go in front of the answer. Hopefully, this is all coming back to you. They're exactly the same principles as what we've learned before, just that you'll have some LNs and some E's hanging around. Now, like we discussed previously, because of the abbreviated AP exam this year, you're not going to have anything that's going to be too hard on the exponential and logarithmic functions. Anything that they do ask will be something that you'll be able to put into the calculator, or it'll be super easy to evaluate. Now, what do I mean by super easy to evaluate? Well, things like, what's the natural log of e? Or what's the natural log of 1? Or what's the natural log of e squared? Those are quantities that you can evaluate. Now, I will say on the AP free response questions, you don't have to evaluate these, but it's possible you could end up with a situation where you have to make a substitution, and it might just be easier on you to go ahead and evaluate them. So let's think about this first one, the natural log of e. What does that mean? Well, remember the base of the natural log is e, so it means e to what power would give you e? Well, e to the first power will give you e. Likewise, e to what power gives you 1? Well, e to the 0th power. And what about this one? E to what power would give you e squared? Well, it would be 2. So this should give you all of the basics for doing simple integration with exponential and logarithmic functions. Your homework was on the first slide, and I trust that this will give